Okay, in the last class we have discussed about the interfacing of A to D converter to 8086. So one of the important parameter of this A to D converter is resolution. How to define the resolution of A to D converter? So if I take the A to D converter, analog input voltage, output is digital. If I take unipolar A to D converter, in case of unipolar, this analog value VA, if I assume that VA, and digital output, if I assume that 8-bit digital output, analog input. As the name implies unipolar, we have only one single polarity, means all positive voltages only. So we will take 0 volts is correspond to 00H, because 8 bits 00H is equivalent to 0000 0000, and 5 volts is taken as FFH, which is equal to 1111 1111. Now to get 00H we require 0 volts. To get 01H, what is the voltage required? 00H will be applied for 0 volts. So what is the voltage required to get 01H? The minimum change in the voltage required to change the position of the digital output. This is what is called resolution. Okay. So how to compute this? So here we have totally 256 levels. This side I will write in analog voltage, this side I will write digital value. This is 0 volts, is correspond to one level, which is 00H. Now what should be this voltage, such that this will be 01H, this will be 02H. What will be the distance between these? How much voltage will be there between two consecutive levels? And this will be FEH, and this will be FFH. This is 5 volts. Okay. So before going for this 8-bit representation, to have the clarity, I will just discuss about the 4 levels basically. Suppose if I represent 0 volts by just only 2 bits 00 binary, 5 volts by 11 binary. Okay. So this 0 volts will be 00 binary, 0 volts, 00, this is 01, this is 10, this is 11. These are all binary values, B, not H. So this is 5 volts. Now what is the distance between two consecutive levels? What will be this? What will be this? What will be this? It's obviously that this is total voltage is 5 volts from here to here, and we have 3 divisions. So each voltage, this one will be equal to 5 by 3 volts. Okay. So if I give 5 by 3 volts at the input change, if I change this input voltage by 5 by 3 volts, then you will get a change of position from 00 to 01 or 10 to 10 or 10 to 11. This is what is called resolution. Now coming over here, so what will be this resolution is, total is, how many levels are there? Here we only have 4 levels, whereas here we will be having 256 levels. This is 256 levels. Correspond to 00 to FFH. Okay. So the resolution of this one is given by, this is 5 volts divided by, we have 3 gaps here, whereas here we will be having 255 gaps. This is the voltage which is required. This voltage is equal to, this is 5 by 255 volts. So in general, the resolution of A to D converter, n bit A to D converter, can be represented mathematically as the full scale voltage divided by 2 raised to the power of n minus 1. So if I take here this case, full scale voltage is 5 volts and this 255 is nothing but 2 raised to the power of, because number of bits are 8, 2 raised to the power of 8 minus 1, which is equal to 255. 2 raised to the power of 8 is 256, minus 1 is 255. So the general formula for the resolution of A to D converter is this: full scale voltage divided by, the full scale voltage need not be 5 volts, we can have 10 volts, 12 volts. Okay. So that full scale voltage divided by 2 raised to the power of number of bit A to D converter minus 1. This is one of the important parameter of A to D converter. So more the resolution is, better is the device, accuracy will be more. Okay. So in order to increase the resolution of the A to D converter, a simple way is you have to increase the number of bits. As n increases, resolution also will increases. But at the same time, the complexity also will increases. So because of this, there will be some compromise between the complexity and accuracy. Resolution decides the accuracy. Okay. Depends upon the applications. The applications where accuracy is more important, we will go for more bits of A to D converters, like in case of biomedical applications, MRI, if I want to convert the MRI information into digital. So in MRI, every sample value is very important. Okay. Even if I miss a small information, so it is going to create a problem. Okay. In such biomedical applications, we will use 12 bits ADCs. And if you take in general image processing applications, so the most of the information will be related to that background of image, which is not important. So 8 bit ADC is also enough. Okay. So this is about this resolution of A to D converter, and we have plenty of applications of A to D converters. So on the other side, as I have told in the last lecture, so most of the real world signals are analog in nature. So we will convert into digital by using A to D converter, and then we will process. After processing, again we have to control the analog devices. So for that we need a digital to analog converter. So the next topic is the digital to analog converter. Also called D to A converter. This is simply reverse to the A to D converter. So the input will be digital, output will be analog. Okay. So if I take this interfacing of D to A converter to the microprocessor 8086, D to A converter is a 16 pin IC, A to D converter is 20 pin IC. 0800 is one of the important D to A converter. This is a DC D to A converter. So, the 16 pins of this D to A converter are, so we will be having 8 bit, this is 8 bit DAC, so 8 bit digital input, D7 to D0. The output will be current rather than the voltage. This is current I out, here I out will be there. This I out is proportional to the digital value. This has to be converted into voltage by using external current to voltage converter, which can be implemented by using operational amplifier. This is V out. This is analog output. And there are some several pins like there will be two reference voltages. If I want to use only one single polarity reference voltage, this other polarity has to be grounded. You have to connect through some resistance. Depends upon this resistance, the I reference current will be changes. So, this pin is V reference minus. We are grounding. V reference plus, we are going to connect through same 2.5 K to some V reference voltage, normally 5 volts to 12 volts. Then the I reference will be given by, this is V reference divided by R reference. So, in this case this is R reference. So, this current comes to 5 by 2.5 kilo ohms. Which is 20 milliamps. Then we have some threshold control signals. This is pin number 1, 3, 16. This is 0.1 microfarads, this is 0.01 microfarads. These are basically used for removing of the noise, and here this will be given to minus 12 volts. And we require a VCC and ground. So, VCC will be, this is VCC pin, this is ground pin. VCC can be plus 5 volts or plus 12 volts. This is totally 16 pin IC. There are total 16 pins. So, this is the pin diagram of the D to A converter. So, there are two types of D to A converters. One is called successive approximation type D to A converter, another is R to R ladder type. Okay. So, here the expression for this I out is, so this digital input, if I call this one as Bn minus 1 is the MSB bit, Bn minus 2, so on up to B1 B0, this is LSB. If it is 8 bit, this will be B7, B6, this is for n bit. For 7 bit, 8 bit, B5, B4, B3, B2, B1, B0. So, this output current I out is proportional to these bits. If all bits are ones, we will get highest current. If all bits are zeros, we will get lowest current. In between, for different combinations we will get different values of the currents. Totally we will be having 256 different currents I out. The expression for this I out is I reference into 1 by 2 Bn minus 1 plus 1 by 4 Bn minus 2 plus so on up to plus 1 over 2 raised to the power of n B0. If it is for 8 bit, so this I out will be n becomes 8. So this is equal to I reference into B7 by 2 plus B6 by 4 plus so on up to B0 by 2 raised to the power of 8, which is equal to 256. So I reference is 20 milliamps. If all the bits are 0 0 0 0, B7, B6, B5, B4, B3, B2, B1, B0. So what is I out? This is current output, this is digital input. This is analog output, which is current here. Okay. So if this is 0 0 0 0 0 0 0 0, if I substitute these values here, if all are zeros regardless of I reference, you will get current as 0. If this is 0 0 0 0 0 0 0 1, what will be the value? So this comes to B7 is 0, all zeros except for B0. I reference is 20 milliamps. Therefore I out is equal to 20 milliamps into 10 to the power of minus 3 divided by 256. This is I out. And if I want a V out, from this V out is equal to I out into 5 kilo ohms. I out into 5 kilo ohms, because this has to pass through this. Okay. So this kilo and milli will get cancelled. 100 by 256. This will be 100 by 256. This many volts will be the output voltage correspond to 0001. This I out is 20 milliamps by 256. Like that, if this is all ones, then this value will be all ones. You have to substitute here, and I reference is 20 milliamps. If I substitute, you will get the corresponding current as well as corresponding voltage. This is how we can convert the digital values into analog, corresponding analog. Okay. Now if you want to connect this to this 8086, so simply you have to connect this to one of the ports of 8255. Okay. So if I take here 8255, I will connect to port A of 8255. So using this 8255, I can give these values. Accordingly, we will get the proportional current, proportional voltage here. Okay. Now suppose if I want to generate square wave. If I connect this V out to the CRO, so I want to generate here square wave with a voltage of 0 volts and 5 volts. Or 0 volts or 10 volts, it is up to you. Okay. Similar to this A to D converter, here also we have unipolar, means 0 volts is correspond to, for unipolar 00 H is correspond to 0 volt, 00 H is correspond to analog output. After this voltage conversion and all, 0 volts, 80 H will be the center point, this will be equal to 5 volts, and FFH is 10 volts. If I use this reference voltage as 10 volts, if I use the reference voltage as 5 volts, this will be 2.5 volts and this is 5 volts, FF will be 5 volts. In case of bipolar, zero zero H is correspond to minus 5 volts and center value 80 H is correspond to 0 volts and FFH is correspond to plus 5 volts. So 00 H is minus 5 volts, 80 H is 0 volts and FFH is plus 5 volts. This is the difference between the unipolar and bipolar. Okay. Here if I want to generate 5 volts, 0 volt, 5 volts, I will take the reference voltage as 5 volts. Okay. So if I send here all zeros over this data bus, you will get 0 volts this line. You call some delay, then again you send FFH, you will get 5 volts. Okay. So I have to program this port A whose address is FCH and controller register address is FFH. So to generate square wave, what you have to do is, first you have to program port A as output port. Okay. Move AL comma 80H, 80H will program all the ports as output ports in mode 0, which you have discussed in earlier lectures also. Then you have to out onto controller register whose address is FFH. Then you take AL with 00 H, this is correspond to this, then out onto port A. So port A is connected to the digital input of D to A converter. Out FCH, which is the address of the port A comma AL. So 0 volts will be outputted on the CRO if I connect this to CRO. Then call delay. This depends upon the frequency of the square wave that is required. Then you make move AL comma FF H out FCH comma AL, then again call delay, so that these two delays are same, so that you will get symmetrical square wave. Then you can write unconditional jump to up. So this up should be here. Again you will take AL with 00 FF. We will take only these two values only. Alternatively we will take 00 FF, 00 FF. So we will not use any other intermediate values. So because of that we will get only either 0 volts or 5 volts, 0 volts or 5 volts. So this is the delay time which is going to decide the frequency of this square wave. So this is how we can generate a square wave using D to A converter. Okay. We can also generate triangular wave as well as sawtooth wave also. Okay. So how to generate a sawtooth waveform? Sawtooth waveform generation using D to A converter. Sawtooth waveform is nothing but So how to change from one level to, if I start with 0 volts and if I take the peak value as 5 volts. So it has to rise in a linear fashion from 0 volts to 5 volts, and then it has to suddenly drop to, this is the x axis, suddenly drop to 0 volts. Again it has to rise from 0 to 5, suddenly drop to 0, 0 to 5, 0, 0 to 5, 0 and so on. So the interfacing connection details are same as the previous square wave generation. There is no change, only the program will be different. So what is the program for this? In case of square wave, we will just output only 0 volts and 5 volts. 0 volts is correspond to 00H, 5 volts is correspond to FFH. Whereas here now we have to change from 0 volts to 5 volts in a linear fashion. Okay. So if I connect the output of D2A converter to CRO, you have to program port A as output port. For that move AL comma ATH out FFH comma AL. This will program all the ports as output ports. Now I will take move AL comma 0 0, then I will output onto port A, whose address is FCH. So with these 2 points is 0 volts, this starting point will be generated here. Now what I will do is I will just increment the AL and I will write the unconditional jump to up. There is no delay here, up is here itself. So first 0 volts will be outputted, then 1 volt, so 0 0 1 H, 0 0 H, then 0 1 H, this is correspond to some voltage which will be decided by the external resistors and all. Okay, 0 2 H, like that. This is 0 volts, this is the value correspond to 0 1 H, this is the value correspond to 0 2 H, 0 3 H and so on. This is the value correspond to FFH. But we are not giving any delay here. How does this linear change will occur on the screen of the CRO? Okay, because inside the CRO there is a linear waveform generator, okay, which will be applied to the X plates of CRO. So because of that waveform, here also the signal that whatever the digital value you are giving, the corresponding analog voltage will be moved in a linear fashion. It will go to 5 volts. Then here what happens is this 0 0, it will go up to FF. If I increment FF further, what happens is it will become 0 0. Means this will go to the starting value, again this will continue in a loop. FF, if I add 1, carry flag will be set, but the result in AL will be 0 0. This is 1 0 1 0. So in AL we have FFH. If I add 1, after that AL will contain 0 0 H. That is why here there is no loop, there is no comparison, just simply I am incrementing AL. I have taken 0 0 H, so it will go up to FF. After that FF, this increment AL operation will make that FF to 0 0, again that 0 0 will be transmitted. So like that you will get a sawtooth waveform. Suppose if I want to generate a triangular waveform. So the difference between the sawtooth and triangular is, in case of triangular we will be having 0 to 5 volts linear increase as well as 5 volts to 0 volts linear decrease. This is the triangular waveform. This is 0 volts, again 5 volts, again from 5 volts to 0 volts, again 0 volts to 5 volts, 5 volts to 0 volts and so on. For this, how to write the program? Connections are same for all the 3 waveforms. The output of this op amp will be given to the CRO. Okay. So only the programs are different. First 2 instructions are same, move AL comma ATH out FFH comma AL, then move AL comma 0 0. So, you will get this point 0 0 point, and you have to increase. So, you have to output this first of all, out port A FCH comma AL. Here also no need of delay, that inside the CRO there will be a linear sweep generator. So, sweep generator will take place, sweep generator will take care about this linear rise, sweep generator inside the CRO. Will causes this linear rise. As well as linear fall. Okay. So, no need of delay here, just simply I will output this 0 0 volts using this instruction. Then I have to increment INR AL, compare AL with FF, because till FF have to use up counting. Okay. Jump not equal, go to up. So, what should do is up, we have to output that value. So, this program will generate a linear change from 0 to 5 volts, this 0 to 5 volts. Once if it is coming out of the loop means this is FF. After that we have to do decrement operation. Okay. Here you have to write DEC, this is INC, DEC AL. So, FF becomes FE, then you have to output onto same FCH. Then you have to compare AL with 0 0. Till 0 0 you have to decrement. From here you are decrementing. So, till 0 0 you have to decrement. So, this 0 0 H jump not equal means it is not equal to 0. You have to go to up 2. So, this up 2 will be, you have to output that value. You have to decrement in the output value. Once if this is equal, then you have to again load with 0 0 and you have to repeat the process. So, for that unconditional jump to up 3. This up 3 will be again, we will load AL with 0 0. Anyhow 0 0 will be there. So, this up will be enough. Because once this is coming out of the loop means AL will be having always 0 0, because we are comparing with 0 0. When AL is equal to 0 0, then only this will come out of the loop. So, AL is already 0 0 is there, no need to jump here. So, we can jump to this up. This up 3 is not required, only up is enough. So, we will go to here again from 0 onwards, we are going to 0 will be displayed, then 1, okay, like that it will display up to 5 volts again. So, this loop will be changes from 5 volts to 0 volts. So, like that we will get triangular waveform. Okay. So, the frequency of this sawtooth or triangular waveform will be decided by the sweep generator of the CRO. It is not there in our hand. Okay. Like in case of a square wave, we can control the frequency of the square wave by changing the delay, whereas here the frequency of the sawtooth waveform and triangular waveform will be decided by the sweep generator present in the CRO. Okay. So, that means so now the simple application of a D to A converter, we can generate different waveforms. Now, using this A to D D to A converters, we can design various measurement systems. Okay. Suppose if I want to measure and control the temperature of a furnace. Measurement and control of temperature of a furnace. Okay. Suppose I have a furnace here. Here you have to insert a sensor, temperature sensor. This is temperature sensor, and here we can control this temperature, maintain the temperature by using a fan and blower and heater. This is heater, this is blower or fan. This is temperature sensor. There are various temperature sensor, depends upon the range of the temperature that is to be measured. RTD is one of the sensors normally used for the lower temperatures. We have thermistor, thermocouple, then we have optical pyrometers, and we have IC sensors also nowadays, IC temperature sensor. This is available in IC form. Okay. So this is range, depends upon the range. Normally for lower range we will use RTD, thermistor. Then for higher ranges, the temperatures of the order of greater than 1000 degrees centigrade, we will use pyrometers. This based on the radiation principle. Because the temperature is greater than 1000 degrees, if I place this any of these sensors, there is a possibility that these sensors may burn. Okay. Because of that, we will use the radiation sensors, where depends upon the radiation we will measure the temperature. Okay. Now again, between these three sensors, this RTD and thermistor, they are all called passive sensors, and this is active. So the difference between this active and passive sensors is, so in case of active sensor, so directly the temperature produces the voltages. So this is according to the Seebeck effect. This operates on a principle of Seebeck effect. So here directly the voltage is produced, EMF, which is proportional to temperature. Whereas in these two cases, the resistance varies with the temperature. So in order to convert the change in resistance, we need some bridge circuits to convert this resistance into voltage. Okay. So that is why they are not called active. Whereas here this is called active because this directly generates the voltage which is proportional to the temperature. Okay. Suppose if I use this RTD or thermistor here, if this sensor is RTD or thermistor sensor, so what happens is, so we will be having two leads. So in order to convert this change in resistance to the voltage, we will connect this to one of the arms of the bridge. We will take a bridge, so we will apply the voltage at this point, some voltage. So these are R. We will assume that the resistance here, because of this temperature, this resistance is proportional to temperature. At room temperature, we will assume that this resistance is equivalent to the other resistances, so that the bridge will be balanced. And if I take the output here, output voltage here will be 0. So if the temperature is other than room temperature, we will get a voltage here which is proportional to the temperature. So this voltage can be converted into 0 to 5 volts range by using amplifier or stages of amplifiers. You can use op amp amplifiers. Now here we are going to have 0 to 5 volts range. So this is all called signal conditioning circuitry. So what is required here, whatever the physical quantity is, so we need to convert the value into 0 to 5 volts, so that I can apply this to the analog to digital converter and I can do the remaining processing. Okay. So let us assume that 0 to 5 volts, this depends upon the calibration. If say for example 0 degrees is correspond to room temperature, or it can be 0 degrees is correspond to 0 volts. Suppose if I want to measure up to 100 degrees centigrade, 100 degrees is correspond to 5 volts, and the corresponding digital values will be 00H, FFH. This is how the mapping will be takes place. This is temperature, this is analog value, and this is corresponding digital if it is unipolar. Now in the digital, so these values can be obtained from this using A to D converter. So you have to connect this to A to D converter. ADC. This is analog input. We will get digital output. This digital output can be read from 8255. The remaining connections of A to D converter I am not showing, because that we have discussed in the earlier lecture. So you have the other connections of this I am not showing, only I am showing the important signals: analog signal, digital output. Then it requires the start off conversion, which is called INTR bar, end of conversion WR bar. This we are connecting to port A. This we have connected to PC3 in our earlier example. This we have connected to PC7. As we have discussed in the last lecture that, so in order to start the conversion, this WR bar should be a low to high transition. We have to apply a low to high transition at WR bar. Then if INTR bar is, this INTR bar is 0, implies conversion is complete. Otherwise conversion is not yet complete, the microprocessor simply waits. Okay. Now if you want to control also, I am using another pin of another port of this one to control this fan and heater. So I will use say PB0, PB7. This I will connect to fan. So I am not showing that connection, I am already just writing. So this point and this point has to be connected. This I am going to connect to heater. So this point and this point has to be connected. Okay. Now I will discuss about how to control this. So I want to maintain the temperature, say between some 30 degrees to 60 degrees centigrade. Okay. So if the temperature is less than 30 degrees, if the temperature is less than 30 degrees, I have to on heater. If the temperature is greater than 60 degrees, I have to on fan. So if this 0 degrees is correspond to 00H, 100 degrees is correspond to FFH, what will be the digital equivalent of 30 degrees and 60 degrees? Depends upon the resolution of A to D converter, right? So here 1 volt is equivalent to 0 degrees is correspond to 0 volts, 100 degrees is correspond to 5 volts. Okay. So we can compute correspond to 30 degrees. So 30 degrees is how much voltage? 100 degrees is 5 volts. 30 degrees is how much? 30 by 100 into 5 volts. This will be 1.5 volts. So 1.5 volts is correspond to what digital value? So each value will be, so 0 volts, if I want to get from 0 0 to 0 1 H, as I have discussed, it is 5 volts by 255. 5 by 255 volts is correspond to 0 1 H. Okay. So 1.5 volts is correspond to, or otherwise 5 volts is correspond to FFH 255. If I take the decimal value, or later I will convert into the hexadecimal. So this 5 volts is corresponding to 255 decimal value. This is 1.5 is correspond to one decimal value, 1.5 divided by 5 into 255. So this will be 5 5s are 5 1s are 51 into 1.5. 51 into 1.5 this will be approximately equal to 51 into 15, 15, 76, 76.5. This is correspond to 76.5. Either you can take decimal value, either you can take 76 or 77, it is up to you. Let us take this is equal to 76, because to convert this decimal number into hexadecimal we need an integer. So 76 if I convert into hexadecimal, sixteen 4s are 64, 12 C is the remainder, 16 zeros are 0, 4 is the remainder, 4 C. So this 30 degrees is corresponding to 4 CH, because you have to compare these values in the program. Similarly, what is hexadecimal equivalent correspond to 60 degrees? So 100 degrees is 5 volts, 30 degrees is this, 60 degrees will be twice this, 3 volts. So this will be 3 volts, this will be 3 volts. So 3 volts means here 3 will be there, twice that of 76.5 into 72, this will becomes 76.5 plus 76.5. 153. So 153 hexadecimal equivalent will be 16 9s are is 144, 144 6 7, 16 zeros 9 9 7 H. So these two values are important. This is 9 7 H. So 4 CH is correspond to 30 degrees, 9 7 H is correspond to 60 degrees. Okay. So whenever this temperature is less than 30 degrees means digital equivalent is 4 C, then you have to on the heater. So you have to actuate, this is the heater which is connected is PB7, we have to send a 1 on this one so that the heater will be on. Otherwise if this temperature is greater than 60, then you have to on the fan, so that it will cool down, it will reduce the temperature. Okay. So the corresponding the program how to control this temperature using this fan and heater we will discuss in the next class. Thank you.